Okay, so far what we have done is we have designed this power stage, at least the first cut working version. Although the efficiency is a bit less than what we would ideally can achieve or would like to achieve, but still this is a first cut working solution. Now what we next need to achieve is we want to ensure that this V out remains at 3.3 volt with a specific degree of accuracy, which is about 2%. So if I look at my specification sheet, I have added this V out DC accuracy to be plus minus 2%. Okay, and this is not a very tight specification, I would say. Okay, so how do we do that? How do we ensure that the V out is stable at 3.3 volt? So inside the ICs, analog ICs, there is a block called voltage reference generation. Voltage reference generation. Okay, and this block actually gives a fixed output voltage. So let's say that output voltage is 1.25 volt. Okay, this output voltage cannot supply any current. The moment you pull out or push in any current into this output, the voltage will suddenly change drastically. But if you do not draw any current, then this voltage is stable at 1.25 and with a very good accuracy. Okay, so in analog ICs, there is a process called trimming, which is done in production generally. Uh, so each part they take and they will measure this voltage and then adjust the internal circuitry in such a way that the error at 25 degrees Celsius for this is brought to a very low value. Okay, so once the IC is manufactured, they will put they will actually power up the IC and observe this voltage, this reference output, and compare it to what the value you want to set it to, and then run a what we call a digital calibration to bring this voltage to a very with us very and bring this voltage very close to the required voltage. Okay, so that process is done, and once that process is called trimming, and once the IC is trimmed out, uh, we will see that the voltage accuracy of this output is very tight. Whether you vary the temperature, whether you observe across, let's say, 100,000, 10,000 units, or whether you vary the supply voltage within the acceptable limit, this output voltage will be rock stable at 1.25 volt with an accuracy of, let's say, 0.5%. Okay, again for a trimmed IC, 0.5% is not considered to be a very state of the art or uh, very extremely tight spec. This is still a very achievable spec. So 1.25 volt plus minus 0.5%. Okay, so we have by design a block which can give us a very stable voltage, and we are going to use this voltage reference to actually set the value of this V out. So what I do is first I resistively divide this V out, this 3.3 volt V out, to create what we call as 1.25 volt rail. So I know that given the fact that I know that my internal voltage reference is at 1.25 and I know the value of V out, I can actually set what should be the ratio of this R1 and R2 so as to create a 1.25 volt. Okay, and then what I do is I compare it with uh, this uh, sort of the uh, reference, and then I push it into a circuitry uh, for further processing, okay, and generate a pulse width modulated clock which directly varies with how much error is there between the voltage reference and this node, okay. So as long as this node is 1.25, okay, so if let's say if this node is not at 1.25, right, then the duty cycle will vary in such a manner that the 3.3 volt is this V out changes, and once the V out changes, this node is brought back to 1.25 by this control loop, okay. So this is a negative feedback loop, and we let's look at it in more detail. So uh, let's first look at uh, uh, pulse width modulation. So what this is a block again inside the control IC. This is also called a PWM uh, uh, generation block. So what this block does is it takes an input, okay, which is slowly varying. Let's say we'll just treat it like a DC signal, call it V control. It takes this signal and gives an output clock, okay, and the relationship between the change in duty cycle of the output clock and the input V control is this, that they are proportional, okay. So this is what we need essentially. We need an output duty cycle which is dependent on the control voltage, okay. So let's see how that is done. It's fairly straightforward, I would say. So I take a voltage comparator, okay, so running off, let's say 3.3 volt, and this is a voltage comparator. So if the voltage on the positive node is greater than the negative volt, output goes high, logic 1, that is 3.3 volt, and if positive input is less than negative input, then output goes low, which is 0, okay. So on one of the inputs, I give let's say I take this negative and give it the V control, and for this analysis I will treat V control is a DC signal and is not varying at all, and I'll call this node B, I'll call this node A, and on node A I give this signal, this is a sawtooth waveform, okay, and this is going from, let's say, 0.5 volt to 2.5 volt, right, or 2.8 volt. So we have left a margin of 0.5 volt with respect to logic 0 and 0.5 volt with respect to logic 1, which is 3.3 volt. This is just an example. I mean, these numbers can obviously change, but what I'm trying to explain is, let's say the V control is at this value. This is V control. Okay, so what will the output look like? So in this part in this time region, the sawtooth waveform, which is the signal A, here A is more than B, okay, and in this region A is less than B, okay. So what does the comparator give as the output? In this region the output will remain high till this region, and once A becomes less than B, then it goes low. So this is the uh, this is what the output clock will look like, or the comparator output will look like. It will obviously be a clock because the comparator has infinite gain, and it goes from 0 to 3.3 volt because the logic 1 for us is 3.3 volt because the supply is 3.3, and there is a finite duty cycle. Now let's say for this okay, yeah, okay, now let's say I increase the value of V control slightly. So let's say I bring it to this new value, which is highlighted in green color. Okay, so I make a change in the V control of delta V. Okay, now I want to see how does the duty cycle change. So I am increasing the value of uh, 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 I'm increasing the uh, control voltage. So if I draw the new clock, right? So the new clock will be something like this. Obviously, because this point where the comparison happens, this has now shifted to a lower value. It has shifted from this point to this point. Okay, the yellow line was intersecting the red line at this point. The green line is intersecting the red line at this point. So the duty cycle actually decreases. Okay, so the duty cycle actually decreases, but what we can see is that uh, if we analyze the whole thing in detail, uh, for a delta V produced, there is a delta T, delta D which occurs, okay, and which is negative. So of course, if we swap the two inputs, sorry, if we uh, if we make this falling slope, instead of falling we make it rising, then this delta T will actually increase, okay. But since I'm just exhibiting the functionality, uh, I'll just stick to this particular case. uh, uh, so let's analyze this region in more detail. So I have this sawtooth waveform, and initially my uh, control voltage was here, and then it moved here, okay. So let's say this is point A, this is point B, and this I know is delta V, right? And this is delta T. X-axis is time, and so this this be theta, then this angle will also be theta, and so tan theta can be written as delta V divided by delta T, and also written as, let's call this V ramp. So it can also be written as V ramp divided by this time duration T. Okay. So from here I can say that delta T divided by capital T is equal to 1 upon V ramp into delta V. So this is nothing but the change in duty cycle, right? So delta D is equal to 1 upon V ramp into delta V control. So what it means is, first of all, that when we change the control voltage, the duty cycle is proportionally varying, and that proportionality factor is 1 upon the amplitude of the sawtooth. Okay. So in this particular case, it will be actually there will be a negative sign also, because when V control increases, the delta D, the change in duty, decreases. Now we will add one more thing to this PWM generation. We'll add a latch at the end. This is reset, and this is set, and this is Q. So this is a SR latch, and this is generally reset dominant. So whichever out of the two, S and R, whichever is having the output of the comparator, PWM comparator, that node should be dominant. Okay. And this is A and this is positive, this is negative, and one of them will have the sawtooth, and this is also called a ramp signal, and this is our V control. Okay. And the way this sawtooth is actually generated is, so what we do is we have a current source. So all of this is inside the analog IC. Okay, this comparator, this SR latch, this voltage reference generation, everything is inside the analog IC. Okay. So as a user, this is generally part of the IC block diagram in the data sheet, but this is very important to understand actually how the whole control works. Okay. So the way we generate the sawtooth is, we'll push a constant current into a capacitor. Okay. And this is negative input, this is positive input, and this is V reference. Okay. Here we can put, so this is again a block diagram, and this is not the actual circuit that will be implementing it. Like this will also work, but this is not generally the actual circuit. And there is a switch here. I can say it's a MOSFET. happens is this is C, let's say this I naught. So when we push a constant current into a capacitor, this voltage node starts to ramp up. So this is initially at 0.5 volt and the capacitor is discharged. So it starts from 0.5 volt and keeps going up. Okay, and this Vref is equal to 2.8 volt. Okay, again this 2.8 volt is coming from a voltage reference. Okay, so we push current into capacitor. This MOSFET is turned off, so all the current starts filling this capacitor with charge, and the voltage starts to ramp up with a straight line. The moment the voltage hits 2.8 volt, what happens is till yeah, I think this should be positive. So till this point, it's ramping up, and the moment it hits the threshold, the comparator output changes, the state changes. So till this point it is actually 0 because the negative input is higher, and at this point it suddenly goes high, and the moment this goes high, this node goes high and it discharges the capacitor. Okay, it discharges the capacitor, and again these are shorted, and again this is running on 3.3 volt. So this goes to 3.3 volt, this goes to 3.3 volt, the MOSFET turns on and it discharges the capacitor to 0 again. So what happens is comes down to 0, and then again the moment this is discharged, so capacitor is discharged, the positive input again falls to 0.5 volt, thereby causing the comparator output to again go low. And the moment comparator output goes low, the MOSFET is turned off and the capacitor again starts to get filled up with the current from the top current source. Okay, so this is how basically fundamentally a sawtooth generation happens. So this is also called astable multi-vibrator. Okay, so this is also called a astable multi-vibrator, or a ramp generator, or a sawtooth generator, whatever name you would like to give it. And if we look at the output pulse, so it goes like this. Goes high at this point and then suddenly goes low, and goes high, then goes low, so on. Okay, so this is this graph in green is the comparator output. So it will this pulse width will be very small. Okay, it will be equal to this pulse width will be equal to the delay it takes from this node going high to this cap getting discharged, and that effect appearing at the output. So this overall delay in the loop is what sets the pulse width of this output of comparator. Okay, so essentially this structure will give two signals at the we'll have two signals. One is the sawtooth So this one is the sawtooth or the ramp, okay, and the second one is the output clock, right. Now here I have drawn for rising uh, ramp. We can do the same for falling ramp. We can actually have a configuration like this and put a current source at the bottom, and this current source is of course coming from the master current reference of the chip, and I have a PMOS, and this is 0.5 volt, and this is internally a 0.5 volt rail, and sorry, this is not 0.5, this is 2.8 volt rail, and this goes to a comparator, and the other rail is 0.5 volt, and then you feed this back. Okay, I have drawn 2 and 3 inverters because one more inversion will come from here through the PMOS. Okay, so the like the delay of inverters is really small, but the delay of this comparator may run into like depending on the technology, like in older technology it can also run into nanoseconds. Okay, so this kind of structure will give you a sawtooth like this, where the output voltage is actually supply referred, the sawtooth is supply referred, and hence with respect to ground it falls. Okay, now we have seen that we have a block which can generate not only the sawtooth but also a clock of very small duty cycle, of course, but it has both positive and negative edges and has exactly the same frequency as that of the sawtooth. Okay, so this we put it in the PW, we put it in front of like this SR latch, we put it in front of the comparator, and this whole circuit is called the PWM generation. This is the PWM generation block. Okay, so we now see that we have a mechanism wherein we can convert a DC signal. We can use a DC signal V control to create a clock with a duty cycle, as a function of V control, and with change in duty cycle being proportional to change in V control. Okay, so this is called the PWM block. This is required because fundamentally we want to sense a DC signal and adjust the duty cycle. So we need to have a mechanism to convert a DC signal into a duty cycle. Okay, now let's come to the various control techniques. So first I will just name them, like broadly name them. Okay, so we have voltage mode control, we have current mode control, and then we have hysteretic control. Okay, and then we can also mix them to get better performance. Okay. So before we start, where I discuss how the exact control scheme that we are going to deploy, let's first start to see uh, like how we there is a need to model the buck converter in small signal, and the reason for that is that the buck converter by its very nature is time invariant system, or for that matter almost every every DC-DC converter is a time variant system, which means it is non-linear, it is large signal, actually a large signal time variant signal, and hence we cannot apply the classical techniques that we know uh, to analyze the system dynamics, because the classical techniques deploy need the use of S transform, and uh, which can only be applied to time invariant small signal uh, systems. Okay, uh, like time invariant linear systems, and this is a highly non-linear system. Okay, so if you look the overall circuit transitions between these two states. So one is this state and the second is this state, and so it's a time variant system. Okay, there is a uh, there is a very specific definition of time variant systems, but I will not get into that. Just explain it intuitively and move on. So let's try to analyze it mathematically. This is VL, this is, and the current going into the capacitor is IC. Okay, uh, voltage across the inductor is VL, and the current going into the capacitor is IC. What I want to do is I want to develop a small signal model for this whole converter. Small signal model means I want to create a linear model, so that I can apply the classical techniques of analysis. Okay, um, so how do we do that? So the uh, let's first write the large signal time variant equations of uh, this whole thing, and it's actually important to be able to do this math. Okay, it's not a waste of time. So I'll go through it. So the voltage across the inductor can be given as V in minus V out. Let's call this signal phi, and this is phi bar when phi is equal to 1, and minus V out when phi is equal to 0. The IL or the IC, the capacitor current, is equal to, let this current be IL, the inductor current, so it will be IL, and the load resistance be R. So IL minus V out by R, and I in, so the input current, the I in is equal to IL when phi is 1 and 0 when phi is 0. Okay, so you can clearly see that VL and I in have two states, so that's why it's a time variant system. It has different transfer function for the two times. Now what I do is I want to convert this linear time variant system into time invariant system. Okay, so I want that these equations should get rid of this phi term. I want to remove this phi term. So what do I do? So I employ a trick. what I do is uh, I'll replace each of the quantities. I'll replace each of the quantities VL, Vin, V out, IL, V out, IC, In. So each of these terms I will replace with the average value of that uh, quantity over one switching cycle of the buck converter. Okay, so uh, like in a buck converter, uh, the switching cycle or the clock which is switching the buck converter, that switching is continuously happening, right? So if I look at one period of that switching, like if I look at one period at a time, so I take 1000 periods of that clock which is switching the buck converter, and I look at each of the periods one by one. Okay, number them 1 to 1000, 1 2 3 4 5 6, and then for each of these periods I I plot the average value of these quantities VL, IC, V in, V out, I in, IL. Okay, that's what I'm going to do. So I will now write the average value in the period. So average value of VL in one period can be written as, so the average value of this guy over the whole period, which is average value of V in minus average value of V out, okay, into T on, because it occurs when T is equal to T on, phi equal to 1 remains for T equal to T on, divided by T. Okay, so this is the average value of this quantity over the whole period, and minus of average of V out into T off divided by T. This is TSW, the clock period, the switching period. So that's what I'm going to do. I'm going to look at the average value of this equation. I'm calculating the average value of this equation over the whole period, over one period of the switching cycle. Okay, so I can just simplify it to, now T on divided by TSW is the duty cycle, so I can simplify it to D into average value of V in minus average value of V out plus T off by switching time is 1 minus D multiplied by minus of V out. Okay, so this is the averaging the first equation of the time variant system. Okay, so as you can see that I have converted this equation, now into I've converted this equation into this equation. So this equation has converted to this equation, right? And in this average equation, now the term phi is gone. Okay, it only depends on it's a single equation and which does not vary with time. Like it varies with time, but it does not vary in a one period of the clock. Okay, and similarly we will do the same for the second equation, which is IC is equal to IL minus V out by R. So I can simply write average value of IC is equal to average value of IL minus average value of V out whole divided by R. So this is my second condition, second equation, and then we'll do the same for the third equation. Average value of I in is equal to T on into average value of IL divided by T off. Divided by TSW plus 0. So which is nothing but D into average value of IL. Okay. So this is the these three equations are actually the uh, uh, time averaged large signal non-linear uh, uh, equation of the buck converter. Okay, so these are time averaged. As you can uh, as you can notice that what we are doing is like we had talked about looking at those 1000 cycles of the buck converter clock. So for each of the cycles, like for the cycle number 1, we average the value of VL, V in, V out, and that first cycle mein we get one value of VL, one value of V out, one value of IC, one value of I in. For the second cycle of the buck converter clock, these values of VL, I in, IC may change, but we will again get one value for each of these variables, and from first cycle to the second cycle these values will change, but for one cycle you will have one set of values. Okay, so we will say that the state of or the values of the buck converter or is varying from cycle to cycle, but for each of the cycles it is constant. So uh, what we will see is that the dynamic nature of the buck converter is still maintained. So if I give a load transient, a sudden step in the load, then the duty cycles should suddenly vary, the V out should suddenly vary, the current should suddenly vary, the inductor currents and the input current. So all these currents should start to vary the moment I give a load step, and that phenomena is actually captured in this set of equations 1, 2, 3, uh, like in the form of R, right? So R represents the load current. If you vary that load current, you can actually plot how the response of the system will be in time domain through these equations, but in a time domain in an average manner. Okay, so you can see how each of the values, the inductor voltage, inductor current, capacitor current, all these values are varying period by period. Okay, so this is a large signal dynamic model, and the only thing it does is it gets rid of uh, the basically the time variant nature, or the second thing it gets rid of is the effects of clock. So if I put like draw draw a circuit which represents this set of equations, or I put these equations into MATLAB or any simulator and simulate, I will exactly get the same behavior what the normal buck converter will have, but there will be no clock. Okay, so it will be much faster. And this is for the CCM mode of the buck. There will be a time averaged model for the DCM mode also. Okay, so we haven't really discussed DCM at all, and I will spend a lot of time on DCM also, but that will be the analysis phase of the buck converter once we have done the whole design. Okay, uh, so now we have the time average large signal behavior of large signal equations of the buck. So we have got rid of the time variant problem, and now we have converted the system to time invariant, and now we want to uh, linearize the system. So the system is still non-linear. Okay, so to linearize it, what do we do? What is the fundamental way in which we linearize any non-linear thing? Like if we have y equal to f of x, right? This is a non-linear relation between y and x. How will we linearize it? We will differentiate both sides. So dy is equal to f prime of x into dx. Okay, so as long as the dx is small, okay, which means that broadly the x value of x does not change, so this remains a constant, then the change in y is proportional to the change in x. So dy is proportional to dx. Okay, and so although the absolute system is non-linear, but the incremental changes in, or the changes, the small changes in the values of input and output are actually following a linear relationship. Okay, so that is what we are going to now apply. We are going to differentiate this set of equations to convert them into linear model. Okay, so let's do that. Okay, so the first equation was VL is equal to D into V in minus V out plus 1 minus D into minus into V out. Okay, so let's differentiate both sides. So I will now call it VL hat. Okay, so derivative of this VL average, I will call it as VL hat. This is just a convention that is there in the textbooks. Now I differentiate this guy, right? So d of xy is equal to d equal to y into d of x plus x into d of y, right? So this derivative will be equal to so different derivative of d, I will call it as d hat. Okay, so d hat into v in minus v out plus d into v in hat minus v out hat. Okay, plus the derivative of this, so minus d hat into minus average value of v out plus 1 minus d into minus v out hat. Okay, so here all the variables which have hat on them, they are actually dx or dy or dz. Okay, derivatives, and the one with angular brackets is the average value of the DC bias point. So let me just simplify this. VL hat is equal to any cancellations happening, so d hat into v in minus d hat into v out. Okay, so I will go slow just to avoid any calculation mistakes. Plus d into v in hat minus d into v out hat plus v out into d hat minus v out hat plus d into v out hat. Okay, so this gets cancelled and this gets cancelled. What we are left with is VL hat is equal to let's combine the equations. D into V in hat plus D hat into V in minus V out hat. Okay, so this is first equation. Yeah, now let's differentiate the second equation of time average model. So IC is equal to average value of IL minus average value of V out by R. So we differentiate both sides, we get IC hat is equal to IL hat minus V out hat by R. Okay, this is the second equation, and average value of I in is equal to D into average value of IL. This implies I in hat is equal to IL into D hat plus D into IL hat. Okay, 3. Now let's apply the steady state equation, steady state condition. So in steady state, uh, the average voltage across the inductor is 0. Okay, uh, and the average capacitor, the average change in voltage across the inductor is in one period is 0. That is the condition of steady state, and the average charge going into the capacitor should always also be 0. If it is not 0, then output will actually go up with every period. So in steady state, VL hat and IC hat should be equal to 0, which means that from this equation number 1, V out hat is equal to D times V in hat, or let's say just yeah, so D into V in hat plus D hat into V in minus V out hat is equal to 0. That is the first condition. IC hat is equal to IL hat, or sorry, this IL hat minus V out hat by R is equal to 0, and I in hat is equal to IL into D hat plus D into IL hat. Okay, so let's draw these three equations into circuits. Let me call this 4, this is 5, this is 6. So let's first draw the equation number 4. I can say that so this is D into V in hat plus D hat into V in yeah, 1 second. Yeah, okay, I have made a mistake. I will not deploy this steady state condition. Instead, I will directly draw the circuits for these three equations 1, 2 and 3. Okay, so for equation number 1, the equivalent circuit I can draw like this. D into V in hat D hat, so this is V in into D hat, and there is an inductor, and this is uh, V out hat. Okay, so this is the equivalent circuit for the first case, equation number 1. The equivalent circuit for the second case, the second equation will be so this IL hat is equal to IC hat plus V out hat by R. Okay, so this is the circuit for this, and this is the circuit for this. This equivalent circuit is this. And for the third equation, I can represent it in this form. IL into D hat is the current source, and the second current source is D into IL hat. This is V in hat, and this is supplying I in hat current. Okay. So this is the equivalent circuit. So what I'll do is I'll draw them again, but in a specific way. So this is V in hat supplying I in hat. I'm drawing this circuit again here. Average value of IL into D hat, and this is D into IL hat, and the next circuit I will draw is this first one. So this is D into V in hat, D into V in hat, and this is V in into D hat, and then we have the inductor, and then we have the V out hat. Okay, so this node is V out hat, and then the third circuit is this, that IL hat should be followed by capacitor and resistor, which means that this IL hat should be followed by a capacitor and resistor. Okay, so this is IC hat. Now we can see that if you just look at this structure, this is nothing but an ideal DC transformer. Okay, with turns ratio 1:D. So whatever the voltage here is V in hat, that gets multiplied by D and comes here, and whatever current is here, right, IL hat, that gets multiplied by D and comes here. So this can be replaced with an ideal transformer. So that gives us the final small circuit circuit diagram, the small signal circuit diagram of our buck converter. This is V in hat. This is the average value of IL into D hat, followed by E transformer, and this is an ideal DC transformer with a ratio of 1:D, same polarities, and this is V in into D hat, followed by inductor, and okay, this is V out. Okay, so this is the small signal model of our buck converter. So as you can see, the input terms are V in hat and D hat. There are two inputs, and the output terms are V out hat. Okay. So a buck converter has actually two inputs, right? It has a V in and it has a duty cycle input or the PWM input, and then we have the V out. Okay, so that is why there are V in hat, D hat, and V out hat. Okay, so if I actually write down mathematically, the V out hat is equal to D into 1 upon S square LC plus R by L into S plus 1 into V in hat plus V in average value into, this is the duty cycle steady state value, into 1 upon S square LC plus R by L into S plus 1. Okay, so this is the overall small signal equation of the buck converter into D hat. So V out is a function of the line voltage change and the control node or the control variable change. And so if we set D hat to 0, then this becomes the line to output transfer function. And if we set the V in hat to be 0, then we are left with the second term, which is called control to output transfer function. Okay, now this is so this is V out hat. Now what we have actually done is, you can see that everything is in S transform, right? So there's S variable everywhere, and we have actually linearized the buck converter, and we have actually got the actual transfer function. So from here you can see that V out hat upon V in hat is equal to D if for DC condition, right? So for DC condition, which is at t equal to infinity, which we already know from before, right? That output divided by input is actually the duty cycle, and that same thing is coming from here. But the additional thing what is coming is the dynamics. So it actually is a second order system. So S square into LC plus R by L into S plus 1. So which means that if I give a small signal step at V in, then the output will not uh, just become D like that, but it will do a second order, settling and those sort of things. And this being a second order system, it will have the quality factor and damping and all those sort of things. Okay, and similarly, the V out hat divided by D hat is equal to V in divided by S square LC plus R by L into S plus 1. Okay, so this is the control to output transfer function, and it depends on V in actually. Okay, so if we recall our what discussion we had done for the PWM block, we had seen that the delta D is equal to 1 upon V ramp into delta V control, right? So if I bring that also in, so let's say if I want to see the transfer function from the PWM input, that's it. That means from V control to V out, then I can replace D hat with 1 upon V ramp into V control hat. Okay, where I am calling delta V as V control hat, because if you remember, the hat represents the small changes in V control. So here I can write V out hat divided by V control hat is equal to V in divided by V control divided by V ramp, which is the ramp height, into 1 upon S square LC plus R by L into S plus 1. Okay, so this is the change, that 1 upon V ramp terms also comes in the control to output transfer function. And there is one very common methodology to improve the performance of a buck converter. What we do is we actually derive the ramp height from V in. So using circuit techniques, we derive the height of the ramp as proportional to the V in value. Okay, so V in is essentially constant, like it's a steady value, so it can change. Okay, but it will more or less remain constant. So let's say input is 5 volt and then the buck converter is operating. So it's not like the input is fluctuating, like goes from 5 volt to 10 volt and then comes back. So it is more or less stable. It is set to a stable value, but that stable value can of course be a different value between the range of 12 volt and 5 volt. Okay, so the V in is actually a steady value. So if I make the V ramp proportional to V in, let's say that proportionality constant is K in into V in. So then what will happen is that the V ramp, you can write, if you write it as K times V in, then it will cancel out, and the V in will cancel out, and the DC value will become constant. Okay, for this term, and we will see that that is actually a good thing, because the duty cycle will become independent of the input voltage. Okay, so if input voltage varies by a large amount, let's say in our case it's varying from 5 volt to 12 volt, which is approximately 2.4 times, then the duty cycle for each of the input values in principle will remain constant. Okay, and that is good from the perspective of optimizing the dynamics of the converter. So this method where we derive VRAMP from VIN is called feed forward compensation. And how do we do that? So this current that we create is essentially a MOSFET. This is derived from VIN. So one very simple way to do that would be, so we put a large resistor, put an NMOS in diode connected fashion, and then we mirror it. Okay, so this is VIN. Let's say it is 5 volt, and this voltage is about like 0.5 volt. Okay, so in this case the current will be more or less VIN by R, this R. Okay, and so this current becomes proportional to VIN by R. So let's say it is just VIN by R, and this VIN by R goes into the capacitor. So what happens is the height of the ramp, okay, or the actually the V ramp will become like a function of yeah, no, I made a mistake again. So what we can do is we can make this reference as derived from VIN, right? So let's say I take VIN and put it through this mirror to generate VIN by R, and then create this voltage Vref. So deriving Vf from directly from Vin, so this is R1, this is R2, so Vref will be equal to R2 divided by R1 into Vin. Okay, so in this particular case like VDD minus actually this thing, so VDD minus R2 by R1 into Vin. So Vref is actually derived from Vin. Okay, and so our VRAMP will actually become a function of Vin. So this is the small signal model of a buck converter, and let's see now how do we control the whole buck converter thing. Okay, so fundamentally this is our buck converter. This is the drive. This is the PWM input, the inductor, the capacitor, and this whole thing is now we have seen is equivalent to V in hat IL into D hat 1 is to D, and minus plus Vn D hat, and this inductor, and then the capacitor, then the load R. Okay, so one change what we can do is, we can do, like, this is just for convenience, not necessary. People sometimes will divide this whole thing by capital D and bring it to the primary side of the transformer, just for the sake of convenience. Okay, so I'll just leave it like that. Now what I want to do is, I want to design the loop. Okay, so I'm designing the loop means I'm only going to concentrate on the PWM input and not on the Vin perturbation. Okay, so I will just remove the Vin perturbation component and ground it. So I will remove this. I'll set the Vin hat equal to 0. So I will ground it. The moment I ground this all the current actually shorts out, and so this whole current can be removed, and this grounds, and the moment this grounds, the whole transformer can be removed. So what I am now left with is this. So this is the small signal equivalent circuit of the buck converter to control to the control input. Okay, so this is the control to output equivalent circuit model, and now we have to basically compensate it. Okay, so let me just plot this guy. So if I look at the Bode plot of this will be flat, and then there will be some peaking because of the underdamped nature, and then this will fall at minus 40 dB per decade. Okay, so this is how it will fall. Now, of course, the x-axis is log of the frequency. This is 20 log of mod of V out, or log of the T of open loop j omega. Okay, so I'm doing the Bode plot of the control to output transfer function, and now once I put the loop right, what will happen is, once I put the loop, there will definitely be a resistive divider, and so let's say this is V out, this is R2, R1, and then is this comparison with Vref 1.25 volt, and then there is some compensator. Okay, and then we have the PWM block, so which is 1 by V ramp, and then the output of this is D hat, which goes back to the power stage input. Okay, so what we have to design is this block, which does the comparison of this feedback voltage with what we want it to be, and then based on that generate a control voltage which varies the duty cycle. Okay, and this whole loop should operate in such a way that the overall phase margin is positive. Okay, so I will uh, yeah, so let's see how we will do this compensator. Now this is the uh, open loop transfer function of the the Bode plot of the control to output. Uh, so I'll take it from this. This is V. Okay, V out hat, or let me call this node. This node is A, and this node is V control. So VA. So this is VA hat divided by V control hat. Okay, so 20 into log of this whole thing, which is a function of S. Okay, so this is what I'm plotting, and this guy is basically V in divided by V ramp into 1 upon that S square term, S square LC plus R by L into S plus 1 multiplied by that resistive division, so R1 divided by R1 plus R2. Okay, so yeah, so this is this term, and we want to now find how to implement this block which takes this VA as input and gives the control voltage as output. Okay, so what we essentially want, that the integrator should look like like the loop should look like a first order system after compensation. Okay, so after compensation, this is what I want the Bode plot to look like. It should be a straight line with a slope of minus 20 dB per decade, a slope of minus 20 dB per decade, and should just go and hit to a point where frequency, which is the UGB point, is roughly equal to the switching frequency divided by 10. Okay, and I'll talk about this, why have we taken this 10, or sometimes we take it to be 20 also. Okay, so why am I so this is the green line represents what we want the transfer function of the loop, the open loop transfer function of this buck converter loop to look like. Okay, after compensation. So how do we do that? So like this is the plant transfer function. This is the transfer function that we want to compensate. Okay, this is what we want after compensation. So how do we achieve? So the Bode plot, that the compensator should look like this. It should fall at 20 dB per decade till this point, and at this point it should have two zeros. The compensator should have two zeros. That cancels out this LC pole, and so the compensator will look something like this. Okay, so it has a pole, the compensator has a pole at DC, so it is falling with minus 20 dB per decade, and then it has two zeros at the LC pole, so it goes up at plus 20 dB per decade. This is just the compensator part. Okay, and our plant is falling at minus 40 dB, so the effective slope now becomes again minus 20. So my plant transfer function starts at this point, the control node, and ends at this point. So this is the transfer function of this is when I go from control node to VA, the transfer function observed is plotted in red here, okay, and with an equation given by this. And my compensator is uh, what goes from VA to V control. The block that goes from VA to V control has a transfer function which is uh, which has a Bode plot given by this, like this. So a pole at DC and two zeros at omega equal to 1 upon root LC. Okay, so it should have two zeros. That is what we want in the compensator. Now let's look at the structure that that does this. Okay, so let's see how we are going to achieve this in the circuit. So before that, like what is the reason that we want this minus 20 dB line? So this is the response of an integrator basically, some 1 upon s into some constant. So the reason is that at low frequencies, which means at DC, we want the overall loop gain to be very high, because that will cause the error to go to minimum, right? Almost to zero, because the gain is very large. So the DC error will go to zero. Okay, and ensuring a minus 20 dB decade line will cause will cause a 90-degree phase margin and will cause unconditional stability. Okay, so that is the reason we want the response of the open loop to look like an integrator. Okay, and the circuit that achieves this is like this. This is an amplifier, not a comparator. This is R1, R1, R2, C1, I'll call this C2, R3, C3. Okay, and this is my V control. So basically, the poles of this system, so it will have two zeros, okay, and three poles, with one pole at origin and two finite poles. Okay, and what are the locations? So Z1 is equal to 1 upon 2 pi R1 plus R3 into C2, which is this. This will give me the first 0, and the second 0 occurs at 1 upon 2 pi R2 C1. Okay, so typically we want both of them to be equal and occur at the LC double pole. So for Fz1 to be equal to Fz2, R1 plus R3 into C2 should be equal to R1 C2, sorry, R2 C1. Okay, so this is the condition for and this should be equal to root of LC. Condition for coincident double zero and occurring at LC double pole. Okay, so thereby cancelling the LC double pole. The pole locations, like since every zero is accompanied with a pole in analog design, so if there is a zero, if there are two zeros, there will at least be two poles. Okay, and there will be a third pole also because there is an integrator being formed here because of R1 and C3. So this R1 and C3 forms an integrator, right? So this is an amplifier. This is an integrator. Okay, so this is an integrator. So here C3 and R1 will form that integrator. Okay, so f of P1 is equal to 1 upon 2 pi R3 into C2. So these two, right? These two will form the one of the poles, and the second pole will occur at 1 upon 2 pi into R2 into C1 C3 divided by C1 plus C3. Okay, so this here the two capacitors come in series, so this loop forms one pole, this forms the second pole. Okay, this loop forms the first zero and this series RC is the second zero. Okay, now if we look at there is one integrator pole also, right? So I'll also mention that FP0 is equal to 1 upon 2 pi R1 into C1 plus C3. So for a general integrator, the transfer function is 1 upon 2 pi RC, right? So that is why I have mentioned this this FP0 as 1 upon 2 pi R1 C1 plus C3. So let me actually draw the Bode plot of just this compensator. So there is a pole at DC, and then the first zero, then the second zero, then the second pole, and then the third pole. Okay, so if I basically extend this line, if I basically just extend this line, it intersects the integrator line, if I extend, it intersects this guy 0 dB line at FP0. This is FZ1, FZ2, FP1 and FP2. Okay, so this is the Bode plot of this block here, this block, empty block, whose input is VA and output is V control. Okay, and I've added this resistance R here so that we can actually get rid of this R2 by R1 division and embed this inside the compensator itself. So these two resistors will form that resistive division. Okay, so once the compensation is done, we can choose the value of R such that this node comes down to be equal to Vref of 1.25 volt. Okay, so this of course this is called a type 3 compensation. Okay, and the compensation, the transfer function of compensating block is of this form. Divided by S into 1 plus S by P1 into 1 plus S by P2 or FP2, P1 FZ1 FZ2. Okay, so let's look at how the overall response will now look like. So our Bode plot of the plant looks like this. This is the Bode plot of the plant, and the Bode plot of the compensator looks like this. Okay, and so the overall Bode plot will look something like this. And here we ensure that this point is FSW by 10, less than that. Okay, the reason for choosing less than FSW by 10 is that we want to remove the since it's a switching circuit, we want to remove the switching artifacts from the Bode plot analysis, so which basically means that we want the signal flow to be much slower by a factor of at least 10 than the rate at which the clock is switching. Okay, so if signal flows less than the signal is flowing at a speed through the loop at a speed which is 1/10 the speed at which the signal is switching, then we can ignore the switching artifacts and treat this whole loop like a continuous time system. Okay, so if you remember that when we had moved from time variant system to time invariant system, at that point itself we had ignored the switching artifacts. Okay, But that as fundamental assumption will only be valid if the bandwidth or the delay through that path is much less than the switching frequency. So that's why we keep it at least at max FSW by 10. Okay, and there is a very famous paper which says that the upper limit on this number, on how much the signal should be slower, should be 6.6. Okay, if we want to have a degradation of less than 10 degrees because of the switching artifacts. Okay, so switching, basically, let me intuitively try to explain why switching causes a degradation in phase margin. So what happens is, if a system is operating on some clock, okay, and so there's a clock here and you have the signal in and you have a signal out. Now this signal will not go from input to output unless the clock comes. Okay, so basically the signal may have arrived early, but it has to wait for that clock edge to come to actually move forward. Okay, so that creates a delay in the loop. Okay, and this delay is can be represented by minus s into ts. S into ts by 2, because it is we'll assume that the delay is not more than 50% of the period, and if we expand it, it can result in a significant sort of phase margin delay degradation. Okay, so we want, this is called a switching artifact. So we don't want this switching artifact to happen. So what we say is that we will ensure that the signal is moving at a speed, like the signal is moving through the loop at a speed which is much less than that of the clock. And so the delay introduced by the clock does not result in a significant phase margin degradation. Okay, so this is just like an intuitive explanation, not, you can't say it is 100% foolproof explanation, but it gives an idea of why switching systems, if you are sort of approximating a switching system in a continuous time domain, which is S transform, then you need to ensure that the signal flows much slower than the rate at which the switching is happening. Okay, and so so I won't go into much detail about the procedure of how to design this kind of compensation technique. So this is called type 3 compensation. So one has to be careful in analog design about the terminology called type. So there is something called an order of a transfer function, and there is something called a type of a transfer function. There is some set of engineers which will treat the type of a transfer function as how many integrators are there in the system. So this system has only one integrator. So some people may call it type 1 system. Okay, but in power electronics, the general convention is that the order of the denominator is actually called the type of the system. So this is a type 3 compensation. Okay, this is also called voltage mode control. Okay, this is popularly known as voltage mode control. So voltage mode control is nothing but this, what we have just seen. Okay, and you can see that this DC gain is actually V in divided by V ramp into this R1 divided by R1 plus R2. Okay, and so if we make, if like V ramp is constant and V in can vary from, let's say, 5 volt to 12 volt, then this DC gain will vary, right? And as this DC gain varies, uh, I mean, uh, the compensation may become a bit difficult. So if I make the V ramp proportional to V in, then this guy becomes a constant. And so this DC value of this plant also becomes constant. And hence, for all the values of V in, this DC gain does not vary. It becomes fixed at this value. And so the compensation becomes more effective. Okay. There's one more advantage of having V ramp kept proportional to V in this kind of a system, and that is the sudden response, the sudden change in duty cycle the moment V in changes. Okay, so let's say we have changed the V in from 5 volt to 7 volt, or let's say there is some slow perturbation at the input. So the system will automatically reject that perturbation if V ramp is proportional to V in. Okay, it will reject in a single cycle, and it will not go through that whole process of second order settling and all. Just in one hit, it will correct it. Okay, so and this process of keeping V ramp proportional to V in is also called feed forward compensation, and this is done in voltage mode control. Okay, so what I have just represented is voltage mode control. Um, it is relatively complex to implement, and thus another problem is that even if we keep the zeros coincident, it may not exactly cancel the LC pole, and that is why we see this kink in the open loop transfer function, because the LC double pole is not exactly getting cancelled by the compensator. Okay, so this is something called a voltage mode control. I will just leave it here. So this is one of the compensation strategies that we can employ in controlling the buck converter that we have just designed. But this has its own set of limitations. One of the main ones being that the switching frequency has to be much less than the bandwidth of the system, the UGB of this loop, should be much less than the switching frequency, and thereby there is an upper limit on the the bandwidth becomes pretty low, so the system response becomes low. And this also has startup conditional stability. Okay, so when the system is starting up, at that point the transfer function becomes less. So we can actually see some sort of a instability only while starting up. Okay, so I'll basically move to the next part of the compensation scheme, which is current mode control, which we are actually going to use in this in our design. But before I get into designing that, let me give you an overview about what it is and the specifics, or basically the theory behind current mode control. So the idea is that in a converter, what we have done in voltage mode control is we have only observed the output voltage and then varied the duty cycle. But the output voltage is not just a function of the duty cycle, right? The output voltage can also be affected by the loop current, this inductor current. Okay, so the basic idea is that instead of just sensing the voltage, output voltage, we should also sense the inductor current and injected part of the loop. Okay, so that's the basic idea that we start with. And the another way of thinking uh, current mode control is that the current flowing through the inductor is actually a sawtooth. So instead of using an a specific block to generate sawtooth waveform and clock waveform, why not use this current waveform, convert it to voltage via sensing, so current to voltage conversion, and then feed it, use it as the ramp for you know uh, doing the PWM conversion. So the first thing is, let me just start with sensing this, or maybe I will start with drawing the model of this current mode control converter. Okay, so uh, let me draw the first the buck converter open loop transfer function. So this is V in hat, and let me just assume that V in hat is 0, simply because we are only interested in designing the loop. So I'll directly write the open loop the transfer function of the buck converter power stage, assuming that V in is constant. So then this becomes V in into D hat, and we have so basically what I do is, so this is the control to output equivalent circuit diagram of our buck converter. So first what I do is I sense the inductor current and convert it to a voltage, and this current to voltage conversion ratio, I called it RMAP, or I will also sometimes use the term RI. Okay, so this is current to voltage, converter, or you can also say current sensing block. Okay, and here maybe I compare it directly with a V control. Okay, and put that SR latch, and then feed it back. Okay, so this is the D hat. So what we are essentially doing is, so there is no compensation in this current loop. Okay, so I have a loop in which I am sensing the current, directly comparing it to V control, and then feeding it back. So this is the reset, and the set is coming from a clock. So this clock is of fixed frequency, generally an RC oscillator, and this oscillator is, again, all of this is inside the analog IC. This current sense may be inside the analog IC, or uh, it may be sensed separately using discrete components, or it can be built into the power stage also. But essentially we need this information of conversion of sensing the current. Okay, so what happens to this loop? So this loop, if you look at it, if you look at the comparator, okay, so the comparator, this is not a comparator, this is an amp, yeah, this is a comparator. So this comparator, or you can say a high gain block. Okay, so what this high gain block will ensure is that this node is equal to this node. Okay, and so what we are trying to do through this whole loop, inner loop, is we are trying to set this inductor current. We are trying to force it to some value using this duty cycle, and that value is nothing but V control divided by R map. Okay, or yeah, so we are trying to set this current to this value. Okay, so V by R is what we are trying to set this current to. So we are employing an internal loop uh, which is actually regulating the current, and then on top of this loop we will have our normal, outer loop, which is much slower and which is generally of this form. Let me first draw it with an op amp. Okay, this goes here. Okay, so let's look at just the inner current loop in more detail first. Okay, so uh, as I had mentioned that basically the uh, the incremental change in the current here, the IL hat is the IL hat now becomes V control hat divided by R map. Okay, so essentially the inductor current is now controlled by this outer loop. Okay, and uh, not by the parameters of this current loop itself. Okay, so what is happening is we are now making the inductor look like in this LC. Now this inductor is not just the inductor, it is actually the loop. Okay, and uh, and this is the D hat and this is a D hat. Okay, so this inductor is now uh, essentially being forced to a current of uh, basically, like, the changes in the inductor current cannot be just determined by this LC interaction, but it is governed now by this control loop. Okay, so we can see that this current is actually this value is actually constant because the outer loop typically has a much smaller bandwidth than the inner current loop. So this inductor now, this inductance, this current now becomes more or less constant, and this inductor now starts to appear like a current source instead of being instead of appearing like a inductor. Okay, so the uh, like for all practical purposes, we can assume that now this LC circuit has now transformed into this kind of a circuit, where the inductor is now a current source with value we control divided by R map, and this is pumping current into the output pole. Okay, so this now becomes more or less a first order system. Okay, now uh, uh, this is like one way of looking at it. Okay, that uh, the loop gain, the loop is trying to the loop is ensuring that these two inputs, the current uh, control loop is actually ensuring that these two nodes are equal, and so if this is V1 hat, then this will be V1 hat, and so the current has to be V1 hat by R. Okay, so this overly simplifies, I mean, what the fundamental problem which we had with the LC was that it introduces a double pole. Okay, now that problem is solved to a great extent by uh, the inductor now starting to appear like a current source, and its current not varying independently by the LC interaction. Okay, so that really improves the dynamic performance of the whole converter. Okay, so let's look at more. Let's analyze the whole inner loop in a bit more detail. So we will look at the inner current control loop from two perspectives. One is in the time domain, and the second is in the frequency domain. Okay, so let me first uh, give some uh, define some variables. Okay, so this is my buck converter, V in into D hat. This is R, and then this is the current sensing. This is R map, and this output voltage is equal to IL into R map. Okay, and then this is basically going to a comparator, and we have a V, I'll call it VFB. Okay, as we'll see, this FB comes from the outer loop, and then this goes to the SR latch. This is D hat. Okay, so and as I'll discuss in a while, that we do something called a ramp injection for stabilizing this current control loop. Okay, for duty cycles above 50% in case of peak current control. Okay, so yeah, so let's look at how this this whole current loop is actually operating. So we have our VFB here. This is the VFB, and so let's say, let me also draw the clock. Okay, so this is the actual PWM clock in yellow color. So when the clock is high, uh, the inductor current actually ramps up. Okay, so the inductor current ramps up. Okay, so as the inductor current ramps up, this node V, I'll call it V sense. So this V sense will also ramp up. Okay, so yeah, I'll directly plot the V sense. So as the when uh, the the clock first goes high, this the inductor, the high side switch turns on, and that causes the current to ramp up. The moment the current hits this the V sense, this is the V sense. The moment this V sense hits VFB, the comparator output goes high. Okay. So as you can see that the VFB is the negative terminal of the comparator, and the this node, I'll call it B. So B is the positive terminal and B is below the negative terminal. So the reset signal is low when the current is ramping up. The moment the V sense hits the VFB, the reset signal goes high, and that causes the high side switch of the buck converter to shut off and the low side switch of the buck converter to turn on, and that causes the inductor current to go down. Okay, and once the inductor current, like the clock period is over and the next positive clock edge comes, then the cycle basically repeats itself. Okay, so the reset signal basically goes high when this the inductor current hits the threshold. Okay, so the inductor current is essentially controlled by the peak value of the inductor current. Okay, so the control is happening when the inductor current hits a peak value of threshold. So that's why this is also called peak current mode control, which means that the inductor current will keep rising till it hits the threshold, and after that the reset signal will be generated that will cause this yellow line to basically go down. Okay, and this yellow line is my duty cycle. Okay, it's not the clock on the S pin. This is the duty cycle which is going to the, or the D signal which is going to the buck converter. the power stage of the buck converter. Okay, so yeah, so this is called peak current mode control, and in peak current mode control, uh, if 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 the duty cycle is more than 50%, then we get into something called subharmonic instability. Okay, I'll talk more about it both from time domain and frequency domain perspective. But before that, let's look at more about instead of directly going into uh, uh, the stability part of the current loop, let's first analyze the uh, loop in more detail. Okay, so I hope you have understood the how the current loop is operating. It is in transient domain. It is peak current mode control, which means that if I have, let me draw the buck, complete buck. Okay, so the way it is essentially operating is uh, the output phi or the PWM signal goes high with the rising edge of the S pin. Okay, so this S pin causes the output to go high, and uh, once the phi is high, this high side FET turns on, and that causes the inductor current to ramp up. So the inductor current ramps up, and with that the V sense also goes up. So this is V sense that I am plotting. So V sense goes up. The moment V sense hits VFB, the reset signal goes high. So till this point the reset signal is low, and at this point the reset signal goes high, and uh, after that this starts to come down. Okay, and it remains high till uh, the next positive clock edge comes on the set pin, and after that it goes low. And once the set pin comes, the phi again goes high, and uh, this current again starts to ramp up. Okay, so essentially the decision to stop, to close the high side FET and turn on the low side FET actually comes from the fact when the V sense node has hit the VFB, which essentially means that it happens when the inductor current has hit some peak value. So that's why this is called peak voltage mode control, sorry, peak current mode control. Okay, so we inject an external ramp into the sensed inductor current. This is again a ramp that we inject. Okay, here it should be. We inject this artificially created ramp which has been created from the same circuit which creates this our, this our, this clock, primary clock of the switching circuit, and this helps in stabilizing the uh, whole buck converter for subharmonic oscillation. The height of this I will call it VEXT ramp. Okay, and so the total amplitude of V ramp total is consisting of the external ramp and the ramp which is created by sensing the inductor current, which is R map into IL. Okay, so this is the total ramp, and of course in this the inductor current ramp quantity will be dominating the overall value. So this is the total ramp. The pulse modulator gain, which is the gain of this guy, is essentially given by the term Fm, which we have seen is 1 upon the total height of the ramp. Okay, so the total ramp with which the VFB is compared to generate the duty cycle, that is my Fm, and again R map is the current sense gain, and we will see that the overall gain of this current loop, the total gain of this current loop is actually nothing but or maybe we'll come to that in a while.